Hello. You have seen this type of tower, and you can see from there they are hanging some cables. In this corridor there are three lines, and each line have a single circuit. You see here one line, two line, and three lines. So this is the three phases. There are other cables on the top. Basically, those cables are what is called shield wires. They are protecting for lighting. So basically, they are not used for transporting energy. They don't need to be thick. There are other type of configuration for building these transmission lines. For example, on the left, we see that we have double circuit. So you have these three lines here, and then you have another three lines. But if you look closely, in general, you don't have like thick cables, and sometimes they are like this composed by bundle of conductors. So basically, this is zoom out of this. How we can model this type of elements of our power systems? We need to think first about what kind of physical phenomena are happening in transmission line. So we know that those lines, when are energized, they are currents flowing. Then when you have a current, so you are expecting to have Joule effect, right? Because we don't have any ideal conductors. This basically will be represented by a resistance. We also know that when we have a current flowing through a cylindrical conductor, it actually is creating a magnetic field. This magnetic field can create a reactance. So reactance will be related with this magnetic field which is created. Also, there are other effects. One is called corona loss. This is basically created when there is a high value of an electrical field. So the air around this electrical field is ionized, that can conduct some energy. But also the losses through isolators. The main function of the isolator is isolate the line from the ground. But the thing is, like, those isolators get dirty, you have salt, you have other kind of contaminant that make the current can go through these isolators. So basically they are creating another type of loss. What we are going to model like a conductance. Finally, because the current can create an electrical field, so this also can be modeled by what is called susceptance. Well, all these phenomena, so physical phenomena, can be modeled in that way. So related with the line, or in series with the line, we have resistance, of course depending on the length. We have this equivalent inductor, which is representing the phenomena of the magnetic field. While in series, or sometimes it's also called in shunt, we can model the susceptance like a capacitive element, and the losses to the ground by these resistant elements. So if we look in the scale of the line, so we can understand them like a one-dimensional element. All these phenomena can be seen like for a delta x of the length of this line, and we can basically make the integration of all these elements through distance of the line. Well, this is very accurate if we have all these values. But we can have some simplification where we are not considering differential of the length, but we are just aggregating all the parameters in just one equivalent impedance for the length of the line and two symmetric admittance. How we are going to compute all those values? Well, there are special methods looking at the geometry of the grid, looking at the temperature, weather conditions, etc. I'm not going to enter into details. I'm more interested in the relationship between voltage and current in one side of the line with regard to the other side. So let's assume we have this two-port model. So here inside there is a line. It could be anything else, but we are going to use this for modeling the line. And then I know, like, well, there are some input voltage, some input current. I use S like a source, assuming like this is a source. And then I have a receiving terminal again, so I can measure voltage and current. So I would like to find a nice relationship between them, ideally in linear form. So this is what is also called sometimes ABCD parameters. So the first simplification, which is very common, is to use just the impedance of the line. And the impedance is modeling only the effect of this magnetic field and the Joule effect. I can compute what is the total impedance of the line by just multiplying by the per unit impedance, small c, times the length of the line. So this is simple for us. And then I can compute what are the values inside of this box. We can compute what is the voltage in the source is equal to the voltage in the receiving part times the voltage drop, and this voltage drop is the current times C. Similarly, we have the current in S is equal to the current in R. This is simple in this case. We can have our matrix in that way. So it's easy to see from this matrix that PS is equal to, so I'm multiplying by this, to BR plus IR times C. This is what I wrote before, and this is basically this voltage drop is IRC. Okay, well, this is a very simple model. This worked pretty well for short length lines for less than 25 kilometers. It is also sometimes called just a model of series impedance, because we have only one impedance in series. Well, there are another model which is very popular. This is the most popular model in modeling power line, which is called pi model. And pi basically because it looks like the pi number. Well, how I can fill this matrix? Well, we can again use the Kirchhoff laws, so voltage law and current law. So I know that the voltage in the source and voltage in the receiving. So voltage in the source will be the what we have in the receiving part plus the voltage drop in this line. Well, here we have BS, and here also we have BR. And what is the drop? So the drop is C, and this is the current that goes through this part of this equivalent circuit. And this is basically IR, which is this, plus the current that goes in this shunt element. So in this shunt element, this current is the voltage in here, in BR, divided by 2 and multiplied by Y. So if I arrange some terms, I can put as a function of BR and IR. But the current is easy, so we have this current in here is equal to the current in this branch or in this shunt, and also the current in this shunt. In both of them, this is with regard to BR and this is with regard to BS. So this is simple. Then basically we can incorporate into the matrix, and then we have this equivalent matrix. So the first observation here is, well, if we don't have these shunt elements, this element and this element, and by the way, I forget to tell you, when we are using this pi model, we are using symmetric shunt elements. So this is why we are sometimes you see Y divided by 2, because Y should be representing the total admittance of this shunt element. So you see, like if I'm decide to simplify not to have this element, I can just see here, like, well, this thing disappears, this thing disappears. Also, this is multiplying, so this thing disappears, this thing disappears, and then I get the previous model, this series impedance model. This model will be very useful. We will use this one in the future. We can think about this differential part, where this is just one delta x of the line, and we can compute more accurate values. We're not going to do this here, but just keep in mind, like, you will keep some elements A, B, C that actually are computed a little bit different way, but this can be just parameter for your model of the line.